The information and examples included in this summary presentation address the topics of data analysis and statistics. Skills to be learned that are associated with these topics are detailed in Objectives 431 to 438. Now, in looking at the course project big picture map, it is worth pointing out that Part 4, the notes and the presentation that you are about to experience, it supports some of the concepts applied in Part 4 of the course project. This is where you're going to propose your data analysis and reporting. And so some of the concepts and ideas that are going to be presented in this presentation can be applied or are applied in some capacity in the project for Part 4. Okay, so the first objective in this section has to do with your ability to distinguish between definitions and examples of statistics versus parameters. This is a very important statistical concept. So a parameter is a characteristic of an entire population. It is a numerical or graphic way to summarize data obtained from the population. So the picture on the screen is a picture from the U.S. Census, and it shows a distribution of average family size. And so all the data from all of the families responding to the census are indicated in this map of the data. So U.S. Census data generally represents parameters of the U.S. population because all of the numbers reflect all of the citizens responding to the census. So here's another perhaps a more clear example of a parameter. This is a distribution of what we call a frequency distribution, and it reflects a normal distribution. This is a picture of the height of all basketball players playing in college in the NCAA. So you will notice from this distribution that there are over 500 players in college who are 6'4", 6'5", 6'7", and 6'8". And I'm not sure what the average height is for basketball players, probably just based on the graph, probably about 6'5". But this frequency distribution represents the data from all basketball players playing in college basketball. All these statistics are reported. And so this would represent a parameter of college basketball players. And I'm assuming these are male basketball players, in the United States. If you were to do a survey of basketball players, in the United States in college, and that survey was collected from a sample of 60 or 70 players, then that data would not be a parameter. In fact, that data would be a statistic. A statistic is a characteristic of a sample from the population. It is a numerical or graphic way to summarize data obtained from a sample. And so on this screen, I just grabbed a screen that reflected the results from a political poll that was done by Elon University in North Carolina. And I'm not sure, this was a poll that was taken between February and March of 2019. And you can see who would you vote for. Now, notice if you can see the tiny little sort of details in the upper right-hand corner of the image. It says North Carolina voters, the N is 914. That means they polled 914 people. So that is not all of the people who are eligible to vote in North Carolina. That's just a sample. So these numbers then represent statistics. Here's another example. This is actual data. And it's a lot of data. This is a picture of the size of shoes that have been sold in the world. This is data that's collected and tabulated by the industries that look at shoes, the big shoe industry, big shoe as they call it. And you can see it's a normally distributed pattern the way it's represented. And you could see that in the world, over 80,000 shoes of size 8 were sold in the world, and I'm not sure what year this represents, but this does not represent the shoe size of every female on planet Earth, because certainly there are a lot of females who did not purchase a shoe, and also there are women who purchased more than obviously more than one pair, so this is a statistic based on a lot of data, but it is still a statistic. Okay, so a lot of the information and examples related to statistics that follow are kind of broken up into two categories. One is called univariate statistics, and that's statistics that reflect data from one variable, like shoe size. That's a univariate statistic. So is the height of a NCAA basketball player. Those are univariate. So there's only one variable. Later on, we'll look at some common statistics for bivariate statistics, and that would be two variables that you examine together. So let's take a look at some of the important information and examples associated with univariate statistics. Okay, so we have, I'm going a little bit out of order in the presentation of objectives, because I want to sort of make sure we're all on the same page about some common definitions that are used in some of the later, some of the other objectives. So you should be able to identify the definitions and examples of the following measures of central tendency. And I'll talk a little bit later about what I mean by central tendency. But these terms are mean, median, mode, and standard deviation. Okay, so let's just refresh our memories then about what those terms mean. And first of all, so measures of central tendency refer to the fact that in a normal distribution of values for a variable, for a single variable, the frequency with which that variable occurs, it tends to there tends to be more values that are closer to the average than there are values that are further away from the average, at least the frequency of values. So and that's called central tendency. And I'll give you an example of that in a moment. So first of all, we have mean, and I'm sure you're familiar with this. This is mean means average. It's the average score of the entire set or distribution of scores. Now, in the literature, mean oftentimes is characterized by a symbol, and it's either an X, a capital X, or a capital M with a line over the top of it. So those are common symbols for a mean or average. Mode is the most commonly occurring score in a sample, and that's an important value to represent in some tests. And finally, median, and that's the middle score in a distribution. So if you line up all of the scores in a distribution or values in a distribution, median would be the one that would be precisely in the middle, given the number of observations in your sample. So those are measures of central tendency, and mean, mode, and median are usually in a normal environment, normal observing nature environment. Those three values are very, very similar. Sometimes they're even identical. Now, variability is different. Variability is how are those values distributed in your collection of observations. And variance refers to the degree of variability of individual scores in your sample, and that again, a common symbol for that is the S squared. That's variance, and then standard deviation is the square root of the variance, often symbolized by SD or by the Greek symbol sigma. Now, the best way to think about standard deviation, though, is just to think of it, even though this isn't 100% accurate, it's the best way to think about it, and that is standard deviation is sort of the average the average variation away from the mean, from the average. What's the average? So, for example, your like every exam that we've had in this class has had an average score, but every student has had a slightly different score, and the distance. If you take the distance from the average for all students, either above or below the average, and you find the average of the differences, that would be the standard deviation. And that's an important value because its value communicates how different are these scores in my sample from each other, or how similar are they. So it's an important statistic. Okay, now in order to better understand those terms and apply them, you should be able to identify the characteristics of a normal distribution curve, or normal distribution. And in order to understand this, I first want to just revisit a graph that I presented earlier to do, a shoe graph, a shoe size graph. And so earlier I presented a graph that communicated total female shoe sales. And again, you can assume that this graph probably reflects roughly the size of feet as well. And this is global shoe sales. So it's based on a lot of data. And you can tell by looking at it that the shape of this distribution it shows you that most of the values clump towards the middle, that central tendency. And in all frequency distributions, or all normal distributions, the variable or the value that you're measuring runs along the bottom axis, and you can see shoe size is at the bottom, and then the frequency of those, or the number or the amount of the occurrence of those values, are always on the left-hand side, on the y-axis, going up and down. So, and again, if you see this graph, just looking at it, you can tell, first of all, that the mean is approximately 8. So the average shoe size is roughly an 8 internationally. And this is a true value based on the data. The standard deviation is around 1.5. And what that means is that the average difference of shoe size from the mean of 8 for females is 1.5 shoe sizes. And so that's the standard deviation, is 1.5. And what's interesting, there's an interesting pattern that emerges that we'll talk about in just a bit. And that is that if you take the mean, the average of 8, and you go plus or minus 1 standard deviation, so that would be a 6.5 as a shoe size, 6.5, to a 9.5. That's 1.5 shoe sizes above and below the mean. And 68% of the population will possess a shoe size between 6.5 and 9.5. And if we were to poll the females in this class, it is very likely that number would be similar in terms of how many had shoe sizes that were either above or below. That would be approximately 68 or 70%. It would also be fairly accurate to predict that 95% of the population would have a shoe size that are 2 standard deviations from the mean. And again, this is a common and recognizable pattern in distributions. So 95% of females possess a shoe size between 5 and 11. And that would, I would guess that number would also apply likely to the students in this class, even with a small n, an n of 30 students, 30 female students. So let's then take a little closer look at what this means. So here is a linear representation of a typical normal bell-shaped curve, or normal distribution. And it's bell-shaped because it's called a bell-shaped curve because, well, I probably don't even have to tell you why it's called a bell-shaped curve. But one thing to note is that in this distribution, in any distribution, typically The mean, median, and mode are values that would be very, very close, if not exactly in the middle of the distribution. So those three values exist there in the graph. And then this just roughly, the values at the bottom are standard deviations, and you will notice that plus or minus one standard deviation from the mean would cover a span that would address approximately 68% of the population. And you can see as you move out, the further you get out, the more standard deviations from the middle, the smaller the population is represented. And that is a characteristic of central tendency and a characteristic of a normal distribution. Here's a different way to look at this distribution. This is a distribution of IQ score tests, and you could see that that 68% of the population has an IQ between 85 and 115. And by the way, the average score of an IQ test, the average is 100 because that's it's a norm referenced value, and they set the average at 100. So this distribution shows you that 95% of the population has an IQ between 70 and 130. And these values are in fact rather accurate for that particular assessment. So again, plus or minus one standard deviation, 68%, plus or minus two standard deviations, 95%. Now, as I mentioned earlier, standard deviation communicates the variation in values in a distribution or from a sample. And in this image, this shows two different shapes of values that would be in a graph, of a distribution graph. And the blue line would reflect a lower standard deviation. In this case, just the value of 4.7 was put in there for whatever this is, for whatever is being measured. Again, the variable is on the x-axis and frequency is on the y-axis. And if you had a larger standard deviation, though, in this case going up to 9.3, you would see a different shape to that curve. Now, this is exaggerated, and the lines, the peaks would be in different locations, but it just shows you that that standard deviation does control the shape of a distribution. And so you were asked to identify the characteristics of a normal distribution of univariate data, and just to summarize then, those characteristics are that the mean, mode, and median are close in value and usually at or near the peak. Sometimes distributions have more than one peak, but typically a normal distribution looks like the graphs that we've been seeing. And again, the mean, mode, and median are at the peak. 68% of the values of the data will fall within one standard deviation of the mean. 95% will fall within two, and 99.7% of the data will fall within three standard deviations. So nearly all values would fall within no more than three standard deviations from the mean. All right, so let's take a look then, spend a little bit of time here looking at bivariate statistics. Again, bivariate means that you're looking at values that you're looking at statistics for two different variables together. Okay, so you should be able to describe a correlation coefficient and corresponding significance level in p-value. So correlation is a measure of relationship, and it's the procedure you use to calculate it is the correlation coefficient. And so correlation is the degree of correspondence between two characteristics of a sample. And the common symbol in the literature for a correlation is R. And the value of the correlation coefficient it goes from +1, which is a perfect positive relationship, to -1, which is a perfect negative relationship. And again, we're talking about correlating two values. So let's just look at a few examples so that you could better understand what correlation is. So again, correlation indicates the relationship between two sets of data, If your correlation graph looks like this, then that's a strong positive correlation. And so if you could just imagine that graph represents two values, and I'll go back to one of the examples that we had earlier, and the value would be shoe size and height, how tall you are. So if shoe size was on the bottom graph on the x-axis and height was on the y-axis, then what the strong positive correlation would tell you is if you had two sets of data from each person that you were collecting data from. One is their shoe size and one is their height. So if you were to plot all of that data, then what a strong positive correlation means is that in general, the taller you are, the bigger the shoe size in general. So a weak positive correlation, the graph would look something like this. And so that might be where there is a relationship, but it's not a very strong relationship between two variables. And for example, if you wanted to do shoe size, if you wanted to go back to shoe size and you wanted to say, well, what other value might actually have might there be a weak correlation, but not a direct one? And it could be related perhaps to like maybe dress size. Yeah, that might be a weak positive correlation. You could assume that people who are taller might have a bigger dress size than people who are more diminutive or smaller. That there might be a weak correlation to that and the shoe size. I'm not sure. Just wanted to keep with the shoe theme. Then there's strong negative correlation, and strong negative means that one value has the opposite of the other value. For example, suppose that you were correlating the number of absences that students had at at school and their overall grades. So if it was a positive correlation, that would mean that the more absences, the higher the value of absences, then the higher the value of grades. But in fact, what you would probably find is just the opposite of that. The higher number of absences would result in lower grades, and so that would be a negative correlation. That's a good example of that. And then there are graphs that would look like weak negative correlations, moderates, and then of course no correlations, data where there's no relationship between two variables. There's probably no relationship between shoe size and IQ, for example. Okay, so let's take a closer look at this and talk a little bit about some of the important values associated with correlations. So again, as I mentioned, degree of correlation is communicated with a value between +1, which is a perfect positive relationship, and -1. So if you take a look at this, here's a graph that shows the relationship between amounts of time studying for research exams and scores on the course exam. So on the left is time studying, and on the right is exam on a research score on a research exam. Okay. So if you were to correlate these values, so what these represent on the left would be students who record the amount of time they studied for a particular exam, just how many minutes did you study, and then you collect the data on their exam score, and you try and determine if there's a relationship between those two. So that's what correlations do. Is there a relationship? Now, from the data, and again, you would have a hard time finding a real good correlation with a limited data set like this, but you could certainly do one in a class of 30. So in this case, the R, or the correlation coefficient, it has a value of 0.74. That's a positive value. It's actually a pretty good, it communicates a pretty strong positive correlation. And that's what the R would represent. If that R was 0.1, that would be a very weak correlation. Now the p-value represents an estimate of the probability that the calculated degree of correspondence between those two variables is actually due to chance. Because it certainly could be due to chance. There could be no relationship between the variables. They could just be due to chance. A p-value of 0.50 indicates that the likelihood of a correlation coefficient calculated is due to chance is 50%. In this case, a p-value of 0.014 means that the probability that the correlation is due to chance is 1.4 out of 100. So that's the probability. And you might be thinking, how in the world could anybody even calculate that from numbers, the probability due to chance? And if you learn more about statistics, it's pretty fascinating because it has a lot to do with variance. It has a lot to do, obviously, with population size and other factors, but it's definitely a characteristic of the numbers. Okay, for 435, you need to be able to identify differences between descriptive and inferential statistics. So if you thought that calculating probability for correlations was magic, inferential statistics is just sort of the, it's beautiful, I think. Okay, so a descriptive statistic is a summary statistic that quantitatively describes or summarizes features of a collection of information. So descriptive statistics describe a population sample. Now, inferential statistics are the statistical procedure used to reach conclusions about associations between variables. They differ from descriptive statistics in that they are explicitly designed to test hypotheses. Inferential statistics allow researchers to make inferences about the relationship between two variables. So just going back, calculating the probability that a correlation is due to chance is actually a descriptive statistic. But if you want to know whether or not your independent variable had an effect on your dependent variable, you would use an inferential statistic for that. So let's take a look at these sort of differences in general. Differences between descriptive and inferential. So in descriptive statistics describe a population sample, that is its variables. They include measures of central tendency, mean, median, and mode, should say median, and measures of variability, variance, and standard deviations. They also include measures of relationships, correlations. Inferential statistics, on the other hand, test hypotheses. You can infer relationships between variables. And there are different tests depending on whether your data is parametric or non-parametric from the population or from a sample. And again, there are different meanings, but you don't need to know so much about that. You just need to know that there are some specific tests that are different. And we'll take a little bit look at the tests that are important in just a bit. So that's the difference between descriptive and inferential statistics. So for 436, you need to distinguish between type 2 and type 1 errors. And this is related to calculating inferential statistics. So for type 1 errors are referred to as false positives. A type 1 error is where the data supports the hypothesis that is tested, even though the hypothesis is not actually true. And again, a lot of statistical procedures are developed so that you can minimize or avoid this type of error. A type 2 error is called the false negative. And the false negative is that the data does not support the hypothesis tested, even though the hypothesis is actually true. So that's a type 2 error. And I have a graphic in the notes that in a humorous way, a picture from a statistics textbook, that a false positive is a doctor telling a man that he's pregnant, an older man at that. A type 2 error is telling a woman who is obviously pregnant that she's not pregnant. That's a false negative. So thought that was kind of clever. Okay, so For 437, you should be able to identify the purpose of a t-test, or it's also called a one-way analysis of variance. So in the t-test examines whether the means of two groups are statistically different from each other. Statistical significance is the likelihood that differences are not the result of either a sampling error or chance. And the use of a t-test, something that I use regularly, is to try and determine whether or not changes between a pretest, where suppose you gave a pretest and you had a mean of 65.7 on the pretest, then you gave a post-test and the mean was 72.3. So that's an increase, that's a difference, but is that a real difference, or is it just in this one sample, in this one instance of measuring, did people just do differently the way anybody would do if they took a test and then took it again? It would just, scores would be different. But in this case, the average scores went up. Is that due to chance, or is that due to the actual data that you analyze? So in this case, if the probability of it being due to chance is 0.03, that p-value, by the way, again, it's going to be based on an analysis that includes the size of the population, certainly the standard deviation, so how variable are the scores, and a few other factors, again, related to variance. So that a p-value of 0.03 means that there's only 3 chances out of 100 that difference in mean is due to chance. So you could, with that number, with that p-value, you could pretty much state emphatically that that scores increased significantly. And that's when we use the word significant. And finally, for 438, you should be able to identify the power of the purpose of calculating the power of a statistical test. So to do this, the power of a statistical test is calculated to determine the likelihood that significant differences observed between groups of subjects do in fact really exist. The power of a test is a measure of its ability to avoid a type 2 error. So in this example of using a t-test to determine if the observed improvement in scores is significant, that is, the same improvement would be seen if you tested again and again and again, the power of the t-test would help you determine if the difference is valid and reliable, if that probability, if that difference really is real. And so you will see the power of a test is often reported in studies, in the statistics that are reported in studies. So again, it's the power is calculated to determine the likelihood that if you do get a significant difference, that difference really does exist. And that's power, and that's the end of this presentation.